This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at iterated integrals and area in the plane. Now take a look at our first problem. And from 0 to x, and 5x plus 3y dx. Now we're used to, with the dx here, we're used to everything being in terms of x's. But here we have the y also, so we have both variables. What we do is you take the integral just like normal for the x, and the 3y you treat as a constant, just the same as if you had just a single number there. So, and then you integrate accordingly. Well, we're taking this one with respect to x. So, the 5x, add 1 to my power, divide by my new power. So that gives us 5/2 x squared plus, and remember, if you just had a constant here, like 5 or 7, then you just add an x onto it, which is what we'll do. So this becomes 3xy. So again, you treat the 3 and the other variable just like constants. And then we want to plug in these, so I'll plug in the x. So I'm going to have 5/2, and I know this seems weird, but we'll put in where the x was, we put parentheses, and then whatever's here we put right here. Plus, and then again where the x is here, we are going to put in the x. That's weird. Where the x was, we put parentheses, and we plug that in. And I'm actually not sure why I put the bracket there. Okay. So this portion right here is for the this portion. Then minus, and then we'll plug in this, the 0. So, and I'll put parentheses around this because that minus has to affect everything that follows it. So again, where we have an x, we'll put in parentheses, and we're plugging in 0. And here, where the x is, we'll put in parentheses, and we're plugging in 0. Well, 0 squared is 0, times 5/2 is 0. 0 times 3 is 0, times y is still 0, so all that drops away. So we're just left with this first part. So that gives us 5/2 x squared plus 3xy. And that's our answer. Let's look at our second problem. 0 to square root of x minus 1, 7xy, and then dy. So we're taking the integral with respect to y. So the 7 and the x I'm going to treat like constants. So we have y to the first power. So again the 7x just remains, times, and we're going to add 1 to our power, divide by our new power. So that gives us 1/2 y squared. Now again, you have to keep in mind that we're integrating with respect to y. So when we plug these in, we're replacing just the y. Well, this becomes 7 times 1/2 is 7/2 x y squared. And we'll plug in the square root of x minus 1. So we're going to have 7/2 x, and then times square root of x minus 1 squared minus 7/2 x, and then we're going to replace the y with 0. Again, these are just definite integrals we're working with here. Though instead of being numbers, we have variables in there. Well, when you square a square root, they cancel each other out. So that gives us 7/2 x times x minus 1. Over here, 0 squared is 0, times 7/2 x is 0, so that all drops away. And if we multiply that through, we get 7/2 x squared minus 7/2 x. And that's our answer. Let me work this one. So I got 0 to 3x e to the x squared y dy. Now again, we're integrating with respect to y, so the x squared part is like a constant. Same, so like if you had a number there. Well, the integral of e to the u is going to be e to the u. But so this is going to be the U-substitution we have to use here. So u is equal to x squared y. We have to do that because we have more than a single variable up here. Now you could rewrite this, assuming that this is a constant, as could you? No, never mind. Long day, I guess. Okay, so then I take the derivative of that. And taking the derivative of that with respect to y. So the x squared is a constant, so the derivative of y is 1. So this just gives us x squared dy. Well, again, keep in mind that this is a constant. We normally can't do this when you got numbers, but I'll put the 1 over x squared out in front. And then inside, I'm going to put in my x squared. And e to the x squared y dy. So again, when we're integrating with respect to y, then the x portion is considered a constant. So again, we let u equal to the exponent. Du would be x squared, because the derivative of y is 1. Then we add on dy. So then this becomes, I'm going to put y's on here. So this is y is equal to 0 to y is equal to 3x. And the x squared y here I replace with the u, so this becomes e to the u. And the x squared dy gets replaced by du. So the 1 over x squared remains out there. Again, I already said that if we had e to the u, the integral of e to the u is e to the u. And that's going to go from y is equal to 0 to y is equal to 3x. Now I need to replace the u before I plug in these values. Well, remember up here we said u is equal to x squared y. So this becomes e to the x squared y. Oftentimes I'll leave these y equals here, or x equals as the case may be in the problem, just so we keep in mind what we're clearly substituting in. We're replacing the y. So this becomes 1 over x squared, and then e to the x squared, and we're replacing the y here with 3x. Minus e to the x squared, and replacing the y with 0. Which gives us 1 over x squared times e. When you multiply these together, we get 3x to the third. Minus x squared times 0 is 0. And anything in the 0 power is 1. So this becomes 1 over x squared times e to the 3x to the third minus 1. And that's our answer. Grab a drink here. Seems weird, I know, because normally you can't treat variables like that. But again, when we're integrating with respect to one variable, the other one's considered a constant. Let me save that. What's this called? Iterated integrals and area in the plane. Calc 3, iterated integrals and area in the plane. I don't have my glasses on, but hopefully I'm spelling everything right there. Page 01.pdf. Okay. And let's look at our next problem. Going from 0 to 3x. And again, we're integrating with respect to y. So let me go ahead and just put y is equal to 0 and y is equal to 3x. It'll help me keep everything straight. So then I've got y e to the negative 3xy dy. Well, if I set the u equal to the exponent here, like the previous problem, well, the derivative of that would give me a negative 3x dy, but I have an extra y here. We have to use by parts here, so integration by parts. And with integration by parts, we have our three columns, SD and I. And the derivative part's going to be the y. And the integral part will be e to the negative 3xy. Now the reason why we do, and this is plus by default, the reason why I choose that is because your d column, your derivative, has to be the part that will disappear. For example, the derivative of y is 1, and then derivative of 1 is 0. See how it goes to 0? If I put the e part here, the derivative of e to a power is e to the power, and derivative of e to the power is e to the power, so it never goes to 0. Now our signs alternate. If that's plus, this is minus, and this is plus. Now we need to find the integral of this with respect to y. Let me do it down here just so we can clearly see it. And then after I do one of them, I won't show all the steps anymore. This is a U-substitution. We let u equal to negative 3xy. And du, the derivative of that with respect to y, well, the negative 3x is the constant portion, so the derivative of y is 1, so it drops away. So we got negative 3x dy. Well, we need a negative 3x in there. Well, we'll put it in there. And we offset it with a 1 over negative 3x out in front. Because again, if you take negative 1 over negative 3x times negative 3x, they cancel each other out. Well, then that gives us negative 1 over 3x, and then this becomes e to the u du. The negative 3x dy gets replaced by du, and then this negative 3xy in the exponent here gets replaced by u. And then the integral of e to the u is e to the u. And then we plug our u back in, and we got e to the negative 3xy. Let me clean that up a little bit. E to the negative 3xy. Okay, so that's this one right here. So this is negative 1 over 3x e to the negative 3xy. So it appears that when we take the integral of that, the e to whatever power stays the same, but we put a negative 1 over 3x out in front. Well, if we do the same thing on this one, this becomes negative 1 over 3x, which is already there, times negative 1 over 3x e to the negative 3xy. Again, the negative 1 over 3x is the constant portion, so just carry it down. And then the integral of e to the negative 3xy, again, gave us the same thing. Well, negative times negative is positive, and we got 1 over 9x squared e to the negative 3xy. Okay. Well, the way the parts goes is we go across like that, and then you go down, and then we go across like this, and then we go down. So, for this problem over here, the integral, we got a plus y times this. Well, a positive times a negative gives us negative. So we'll have negative y over 3x e to the negative 3xy. So again, I took the y times this, and I just put the y up on top. Then minus 1 times this, well, this is 1 over 9x squared. So minus, and the 1 doesn't do anything, so this just becomes 1 over 9x squared e to the negative 3xy. And from y is equal to 0 to y is equal to something. Y is equal to 3x. Hopefully you remember the integration by parts, use the table method. If not, then take a look at the lesson back in... actually, I haven't created it yet for Calc 2. But I will get there eventually. Now keep in mind what we're plugging in here. We're plugging in the y equals, so we're replacing the y part of this. Well, they both have an e to the negative 3xy, so I could factor that out in front. Probably wouldn't help me a whole lot. Trying to think the simplest way to do this. Yeah, I'll go ahead and bring it out in front. So I got e to the negative 3xy, and then here that leaves us negative y over 3x minus 1 over 9x squared. And again, we're replacing the y, so let me first plug in the 3x. So this becomes e to the negative 3x times y, which we're putting in 3x. And then replacing the y here, so this becomes negative 3x over 3x minus 1 over 9x squared. Now notice the 1 over 9x squared doesn't change at all because it doesn't have a y in it. Minus, and again, we're replacing the y, so this becomes e to the negative 3x times 0 times negative 0 over 3x minus 1 over 9x squared. Negative 3x times 3x gives us negative 9x squared. These 3's cancel, this x cancels, so that gives us negative 1 minus 1 over 9x squared. Negative 3x times 0 is 0, so this is minus e to the 0. And negative 0, 0, 0 divided by 3x is 0, minus 1 over 9x squared, which gives us e to the negative 9x squared times negative 1 minus 1 over 9x squared. Now e to the 0 is 1, so that drops away. And here we have a negative negative, which gives us a positive. So we're going to have plus 1 over 9x squared. Now it doesn't really benefit us to combine these at this point. Because if I try to combine these, this one we can't combine here because it has e to the negative 9x squared with it. But that'd be our answer. Assuming no basic algebra mistake, or basic calculus mistake, even for that matter. Let me double check everything. Let's see, negative y, okay, minus that, then replacing the y. Okay, that looks good. Let me save that. There we go. And let's take a look at our next problem. This one introduces double integrals and how to do that. Okay, now leave a little bit of room here. 4x minus y, and then dy and dx. Well, the inner one, the dy, corresponds with this integral symbol here. Since this is dy, then these will be y equals here. And I'll put it in that form just so we can clearly see everything. And that goes from 0 to 3. Now our outer one is the dx, so these are going to be x equals. And that'll go from 0 to 2. Well, what we do is we take the integral of the inside one first. So it's like I'm ignoring the outer one, so it just carries down. So we're going from x equals 0 to x equals 2. And take the integral of this. And again, we're doing it with respect to y, so the x is a constant. So I got 4x here. So this becomes 4xy. Again, if you just had a single number here, like 7, then all you do is add a y. And that's what we did here. Minus y, this is y to the first, so we'll add 1 to our power, divide by our new power. So that's 1/2 y squared. And from y is equal to 0 to y is equal to 3. Well, now we want to plug these in. And again, keep in mind what we're doing. We're plugging these in for y. So this becomes 4x times 3 minus 1/2 times 3 squared minus, and then I put a parentheses because this has to affect everything that follows it. I put 0 in for y. So I got 4x times 0 minus 1/2 times 0 squared and dx. Okay, so we got 4x times 3 is 12x. 3 squared is 9 times 1/2 gives us negative 9/2. Now 0 times 4x is 0, so that drops away. 0 squared is 0 times 1/2 is 0, so all that drops away. So then we just got our dx here. Well, now we want to integrate with respect to x. Again, here we have x to the first power, so we got 12 times 1/2 x squared. We add 1 to our power, divide by our new power. Minus, and if you just got a constant, then you just put the variable on it. So minus 9/2 x. From x equals 0 to x equals 2. Well, now we'll plug in these values. 12 times 1/2, actually let me simplify a little bit. 12 times 1/2 is 6. So that's 6x squared minus 9/2 x. X equals 0 to x equals 2. So plug these in. So put 2 in, so we got 2 squared minus 9/2 times 2 minus, and then I'll plug 0 in for the x. So I got 6 times 0 squared minus 9/2 times 0. 2 squared is 4 times 6 is 24. These 2's cancel, so I got minus 9. And 0 squared is 0 times 6 is 0, so it drops away. 0 times 9/2 is 0, so it drops away. So if I subtract that, assuming I don't get any kind of basic mistake anywhere up above, 15 is our answer. Let's save that. There we go. And let's look at our next problem. Okay, so we got the outer one is the x this time, so we got x equals 0 to x equals pi over 2. And then our inner one's going to be the dy, so this will be y is equal to 0 to y is equal to 2. In these first problems, we're just kind of practicing the iterated integrals. What these will really represent is we're trying to find area And for this first section, we'll pretty well just, I think there's a couple problems at the end where you have something beyond just a 1 here. But these are going to be our restrictions, that we're looking between x is equal to 0 to x equals pi over 2, and y is equal to 0 to y is equal to 2. And we're trying to find the area, eventually the volume, that goes along with these. So that's the idea behind this. Because remember, when you're dealing with one dimension, back in Calc 1, that's where we're finding area. Well, again, I'll look at the inner one first. So I'm going to look at this right here. And I'm taking the integral with respect to y, so the sine x is just a constant. So it doesn't change anything, just stays there. You could even put it out in front of this integral right here if you wanted to. So it gives us x equals 0 to x equals pi over 2. And I'm looking at just the y part, so we'll add 1 to our power, divide by our new power. So that gives us 1/3 y to the third sine x. Y is equal to 0 to y is equal to 2. Now we're going to plug in those values. And again, keep in mind what we're plugging in here. These are y values. We're plugging in y is equal to 2 and y is equal to 0. So where the y is, we'll put in 2. So I got 1/3 times 2 to the third sine x minus, and then I got 1/3, and where the y is, I'll put in 0. So 0 to the third sine x. Well, the 2 to the third is 8, times 1/3 is 8/3. I could put it completely out in front if I wanted to, or leave it inside here. And then we got sine x. Now 0 to the third is 0, times 1/3 is 0, times sine x is 0, so that all drops away. So we're left with this right here. Again, if you want, you can take the constant, the 8/3, put it out in front. And the integral of sine x is negative cosine x. And again, we're going to be plugging these in. Now the negative I can put clear out in front with 8/3. So that gives us negative 8/3 cosine x from x equals 0 to x equals pi over 2. And now I'll plug in those values. So I got negative 8/3 times cosine of pi over 2 minus cosine of 0. And if we look on our unit circle, here's pi over 2, and this point would be 0, 1. And this point over here is 0, which would be 1, 0. When I say 0, I'm talking about the angle. Now remember, cosine is the x part of our point. So cosine pi over 2, our x part is 0. So this would be 0 minus, and cosine of 0, again, cosine is the x part, which is 1. So that's 1. And 0 drops away, and negative 8/3 times negative 1 gives us a positive 8/3. And that's our answer. Grab a drink here. Let's look at this next one. Okay, so our outer one is the dx. So this will be the 0 to 3 will be x equals 0 and x equals 3. I would definitely recommend, until you get comfortable with those, put those on there. It really helps keep everything straight. The inner one is a dy, so that'd be y is equal to 0. to y is equal to square root of x. And then I got y e to the 3x dy dx. Okay, so I'm going to work with the inner one here. I'm going to take the integral of this with respect to y. So the e to the 3x is just a constant. And I'll go ahead and show it in this example. Again, since the e to the 3x is a constant, I can put it out in front of that particular integral if I wanted to. Now you can't put it clear out in front, but you can definitely put it out in front of this because I'm integrating with respect to y. And dy dx. So this is what we're working with. No, this does come out nice. So I was sitting there thinking, oh, this comes out hideous, but no, it comes out nice. Okay, so I got x equals 0, and x equals 3, and then e to the 3x. And then the integral of y, add 1 to your power, divide by new power, so that's 1/2 y squared. These right here. Now the 1/2 I could put completely out in front if I wanted to, and so I don't never have to worry about it. And we got e to the 3x here. Okay, so we're left with the y squared inside. So we're going to plug in these. So I'll put in the square root of x in for the y. So we got square root of x squared. Minus, I'll put 0 in for the y. So we got 0 squared. Of course, the 0 squared drops away. And when you square the square root, they cancel each other away. So we're left with x e to the 3x dx. Well, this is another one by parts, using the table method. So I'll do it over here. I got s d I. Now our derivative will be the x, because again, it has to be the part that when you keep taking derivative goes to 0. Well, derivative of x is 1, and derivative of 1 is 0. This is always plus, then it alternates, minus, plus. And here we're going to have e to the 3x. And again, what we're doing there is we're taking the integral of e to the 3x with respect to x. Well, this would be the U-substitution. We would set u equal to 3x, du would equal to 3 dx. So we need a 1/3 out in front and put a 3 inside. And then this would become 1/3, and then the 3 dx gets replaced by du, and the 3x gets replaced by u. So this looks like e to the u du, which gives us 1/3 e to the u. The integral of e to the u is e to the u. And we said u was 3x. So this is 1/3 e to the 3x. Well, let's look at that. 1/3 e to the 3x. Basically, when I took the integral of e to the 3x, I just put a 1/3 in front of it. So when I take the integral again, this 1/3 right here just carries down, and then the integral of e to the 3x is 1/3 e to the 3x again, which is 1/9 e to the 3x. Again, with the integration of parts, we'll go across like that, and then go down, and then we'll go across like this, and go down. Oops. All the way down to here. So this becomes 1/2 stays out in front. If I go across, I got plus x times 1/3 e to the 3x. So that gives me 1/3 x e to the 3x. Minus 1 times 1/9. So that gives me a negative 1/9 e to the 3x. From x equals 0 to x equals 3. Well, now we're ready to plug those in. 1/2 stays out in front. So I'll plug 3 in for the x. So I got 1/3 times 3 e to the 3 times 3 minus 1/9 e to the 3 times 3 minus, now I'll plug the 0 in for the x. So I got 1/3 times 0 e to the 3 times 0 minus 1/9 e to the 3 times 0. Okay, so I got 1/2. 1/3 times 3 cancels, and so we got e to the 9th minus 1/9 e to the 9th. Over here, and then we've got minus 0 times 1/3 is 0 times e to the 3 to the 3 times 0 power. All that goes away basically. So we got a negative negative. So this becomes a positive 1/9, and then 3 times 0 is 0, so we got e to the 0. Which gives us 1/2, and this would be the same as 9 over 9, e to the 9th, minus 1/9 e to the 9th. Now e to the 0 is 1, so that just gives us 1/9 times 1, or just 1/9. So that gives us 1/2, and these both have e to the 9th, so 9/9 minus 1/9 is 8/9. So we got 8/9 e to the 9th plus 1/9. Now I could factor out a 1/9 if I wanted to, but let me show what it looked like. If I factor out a 1/9, this would give me 1/18, and this would be 8 e to the 9th plus 1. So either one of those is your answer, whichever form you choose. Let me save that. And let's look at our next problem. And let me grab a drink here too. Here we got different variables, but it doesn't matter what variable we're dealing with, same idea. Now our d theta is on the outside, so this is going to be theta is equal to 0, the theta is equal to pi over 2. And on the inside we have our dr, so this will be r is equal to 0 to r is equal to sine theta. And we got r to the 5th cosine theta dr d theta. Again, I'm going to work with the inner one here. I'm integrating with respect to r, so that means the cosine theta is a constant. So I could put it out in front of the integral if I wanted to this, but I'm going to leave it inside and just keep in mind it's a constant. So integrate in respect to r. So we got r to the 5th. We'll add 1 to our power, divide by our new power. So we got 1/6 r to the 6 cosine theta. And then from r is equal to 0 to r is equal to sine theta. Now again, I put these r's here to really emphasize it, because what we're doing is we're replacing the r with these. The theta we don't change at all. Now the 1/6 I can put completely out in front, so we don't need to worry about it. And then I'm going to plug in sine theta for the r. So this gives me sine theta to the 6th power cosine theta minus, and here I'm plugging 0 in for the r. So I got 0 to the 6 times cosine theta d theta. So we got theta is equal to 0, theta is equal to pi over 2, and then we got sine theta to the 6th power, cosine theta. Now here we got 0 to the 6th, which is 0, times cosine is 0, and so that drops away, d theta. Well, now we're ready to take the integral of this. And this is a U-substitution. Remember, if you have parentheses to a power, you try to let U equal to what's inside the parentheses. So U is equal to sine theta. Derivative of that, du, the derivative of sine is cosine theta d theta, which works out really nice because we have a cosine theta d theta there. So this becomes 1/6. Theta is equal to 0 to theta is equal to pi over 2. And this becomes u to the 6 du. Well, we add 1 to our power, divide by our new power, so we got 1/7 u to the 7th. Theta is equal to 0 to theta is equal to pi over 2. Again, I cannot plug these in because we're plugging them in for theta, so we need to plug our u equals back in first. So we'll put that in. Actually, I'm going to go ahead and put that 1/7 out in front. So 1/6 times 1/7 gives us 1 over 42. And we're left with the u to the 7th. The u was sine, so we got sine theta to the 7th. And theta is equal to 0 to theta is equal to pi over 2. And now we're ready to plug those in for theta. So we got 1 over 42, and then sine of pi over 2 to the 7th minus sine of 0 to the 7th. Now if we look on our unit circle, here's pi over 2, and this point would be 0, 1. And here's 0, or our angle 0, and this point would be 1, 0. So, sine of pi over 2. Sine is our y, so which is 1. So we're going to have 1 to the 7th minus, and sine of 0, again, sine is our y, which is 0, so we got 0 to the 7th. So that drops away. 1 to the 7th is 1 times 1 over 42 is just 1 over 42. And that's our answer. So we save that. Tablet to blow up, so I'll bring up another copy. There we go. And let's take a look at this one. This is showing how to handle an improper iterated integral. So we got, and again, I'll keep in mind what these are. So the outer one is a dx, so this is x equals 1 to x equals infinity. And the inner one is a dy, so this is y is equal to 0 to y is equal to 2 over x. 5y to the 4th dy dx. Now again, we're taking a look at the inner one here. And the 5 I could put completely out in front, so let me go ahead and do that. And then the integral of y to the 4th, you add 1 to your power, divide by your new power, so that's 1/5 y to the 5th, from y is equal to 0 to y is equal to 2 over x dx. Church is ringing its bells. Must be having a Good Friday service. Now the 1/5 actually I could put completely out in front. So should have, could have. Okay, so we got 5 that's already out there, and then we move that 1/5 out in front. So we're left with y to the 5th here. So plug in these values. So put the 2 over x in for y. So we got 2 over x to the 5th minus, and I'll put the 0 in for the y. So we got 0 to the 5th dx. Well, 5 times 1/5 cancels. And we're going from x equals 1 to x equals infinity. And 0 to the 5th drops away, so I'm left with 2 to the x to the 5th. 2 to the 5th is 32. And x to the 5th dx. Now, we can take 32 and put it completely out in front if we wanted to. And x equals 1 to x equals infinity. And we're left with 1 over x to the 5th dx. We would like to have it as x to a power. Makes it real easy. So we can rewrite this as x to the negative 5. Again, when you move something opposite where it's at in a fraction, the sign of the exponent changes. So then we'll add 1 to our power, divide by our new power. So add 1 to our power and divide by our new power. X equals 1 to x equals infinity. Now that negative 1/4 I can put out in front. So we've got 32 times 1 over negative 4. And we're left with the x to negative 4 inside, and I can put it back down in the denominator, and it becomes 1 over x to the 4th. X equals 1, x equals infinity. Now this is an improper integral. And what we're really doing, 32 divided by negative 4 is negative 8, is instead of plugging in infinity, we're studying the limit as another variable, like b, goes to infinity. And so then we've got 1 over x to the 4th, and we're plugging in x equals 1 and x is equal to b, because you can't plug infinity in. All you can do is study the limit as it goes to infinity. So we'll do this. We got limit as b goes to infinity, and then we'll plug the b in for the x. So we got 1 over b to the 4th minus 1 over 1 to the 4th. Again, we're plugging in the 1 there. I better continue it up here, which gives us negative 8. The limit as b goes to infinity of 1 over b to the 4th minus 1 to the 4th is 1. 1 divided by 1 is 1. Now, if we did plug that in at this point, technically we're not actually plugging it in, we're studying it as it goes to infinity, but for purposes of this problem, the same idea. If we put that in for the variable, we got infinity to the 4th, and 1 over infinity is always 0. So this is negative 8 times 0 minus 1. Now 0 drops away, and negative 8 times negative 1 gives us a positive 8. And that's our answer. Let me save that. And let's look at our next problem. We got 4x minus 3y equals 0. And x plus y is equal to 7. And y is equal to 0. The instructions here are use an iterated integral to find the area of the region bounded by the graphs of the equation. We saw how to do this back in Calc 1, I think. This is a different way of looking at it. to see how to do it. And again, we're going to use iterated integrals to do this. Well, first off, I need to find out what these graphs look like. So let me go ahead and solve both of these for y. So we got 4x equals 3y. Divide both sides by 3. And we got y is equal to 4/3 x. Now this one I can take the x over, and it becomes a negative x plus 7. Picture is real important on these. Helps you understand where everything's coming from and so forth. Let me do the y is equal to negative x plus 7. 2, 3, 4, 5, 6, 7. And can't draw a straight line, but I think you get the idea. That's y is equal to negative x plus 7. And the 4/3 x. Well, see, 1, 2, 3, 4. 1, 2, 3. This one is the y is equal to 4/3 x. And then the y is equal to 0. Well, that's it. This right here. Y is equal to 0. So what we're taking a look at is this right here. So this is what we're trying to find. So we're going to set up our integration. Now, to do our integration, we have to find out what this point is right here, and what this point is, and what this point is. Some of them you can, by inspection, you can look at it and see. Like this one's obviously x equals 0 and y is equal to 0, though the x is the only thing we're really concerned with. This one, yeah, you can probably look at it and see, okay, it's x equals 3. But let's say I can't see that. We're going to find the point of intersection of the red line, which is y is equal to negative x plus 7, and the blue line, which is y is equal to 4/3 x. So that's this one right here. Well, what we do is, since they're both y equals, I can just equate them. So I got negative x plus 7 equals 4/3 x. That's the substitution method. Multiply both sides by 3, or multiply everything by 3 to get rid of the fraction. So that gives us negative 3x plus 21 equals 4x. Take negative 3x over, and we get 21 is equal to 4x plus 3x. And we got 21 is equal to 7x, or if we divide both sides by 7, we got x is equal to 3. So this point right here, not that we need the y part, but this would be 3 comma something. And if I put 3 in for the x here, negative 3 plus 7 is 4. So this would be 3, 4. Okay, now we need to find this point right here, which is the point of intersection of the red line, which is y is equal to negative x plus 7, and the green line, which is y is equal to 0. Well, again, they're both solved for y, so I just equate them. So we got negative x plus 7 equal to 0. Take negative x over, and we get x is equal to 7. So this point right here is going to be 7, 0. And by inspection, it's obviously this one is 0, 0. Now, if I didn't see that, then I could find a point of intersection, the blue line and then the green line. So set those equal to each other. Okay, why is this important? Well, for my area, I'm going to look at my x values. So I'm going to go from x equals 0 to x is equal to 3. So I'm going from here to here. Now the way you do that is you set your smallest x value, go into your largest x value, And always what you put on the outside here when you're dealing with area and so forth is these have to be numbers. Now look at our y part. If I'm just looking at this first half, and let me draw a little black line here to separate them. Okay. I'm looking at this first half right here. This blue line is above the green line. So the green line is less, which means this green line is y is equal to 0, and the blue line is above that, so it's greater than. So that's going to be y is equal to 4/3 x. Again, that was our blue line. And then we'll have dy dx. Now that handles our first half of the triangle. Then our second half of the triangle, this is going to go from 3 to 7. So we got x equals 3 to x equals 7. And this right here is our, again, our y is equal to 0. And the red line is up above that. And what was our red line? Negative x plus 7. So y is equal to negative x plus 7, or 7 minus x. However you want to do it. And then dy dx. So again, you're looking in terms of your y values. This always has to be a smaller one. This is your larger one, smaller one, larger one. In terms of the x and y, I should say. Smaller, larger, smaller, larger. Now you could have also set this up differently. Instead of having the x values on the outside, you could add the y values. Now sometimes it's easier to do that, sometimes it's harder. You know, you have to look at the problem and see which one has the easier setup. Now if I looked at the y values, it looks like the y values would go from 0 to 4. And then for the x values, you'd have to solve these for x, and this one's further to the left, so it's a smaller, and this is one further to the right, so it's a larger. So you'd have from x equals this to x equals this, which instead of having two separate integrals like this, you'd have one. But anyway, I set it up this way, so I'm going to go and work this. Well, we'll look at the inner one here. So the x equals 0, x equals 3 carries down. Well, this is just like a 1 here, so the integral of 1 is y. So this becomes y from y is equal to 4/3 x, or y is equal to 0 to y is equal to 4/3 x. Same thing here. We're going to work with the inner integral. So this remains x equals 3 to x equals 7. And again, there's like an invisible 1 here, so the integral of 1 is 1y, or y, from y is equal to negative x plus, or y is equal to 0 to y is equal to negative x plus 7. Well, we're going to plug these values in for our y. So this is going to be 4/3 x minus 0 dx. Again, I'm plugging the 4/3 x in for the y, minus, and I plug 0 in for the y, plus, and then x equals 3 to x equals 7, and I'll plug that in. So we have negative x plus 7 minus, and then I'll plug the 0 in for the y dx. Well, the 0 drops away, so I'm not going to write it, but we'll ignore it. And now I'm going to take the integral with respect to x. So this gives me, actually, let me put the 4/3 out in front. So we'll have 4/3 there. And then the integral of x is, you add 1 to your power, divide by a new power, so that's 1/2 x squared, from x equals 0 to x equals 3. And on this one, the negative x, that becomes negative 1/2 x squared. Again, add 1 to the power, divide by a new power, plus, and then we put an x on the 7. And this will go from x equals 3 to x equals 7. And if I plug in my numbers, actually that 1/2 I could move out in front. So 4/3 times 1/2. And if I plug 3 in for the x, I'm going to have 3 squared minus, put 0 in for the x, so 0 squared, plus, and put the 7 in, so we got negative 1/2 times 7 squared, plus 7 times 7, minus, and then we got negative 1/2, and I'll put 3 in for the x. So 3 squared plus 7 times 3. Well, 0 squared drops away. This 2 reduces with this 4, so that gives us 2/3. 2/3 times 3 squared, which is 9. And then we got 7 squared, which is 49, times negative 1/2. That gives us negative 49 halves. Plus 7 times 7, which is 49. Minus 3 squared is 9, times negative 1/2 is negative 9 halves. 7 times 3 is 21. This gives us 6. Minus 49 halves plus 49. Negative flips a sign, so it becomes a positive 9 halves minus 21. 49 minus 21, I'll probably make a basic math error here. 28 plus 34, or 6 is 34. Negative 49 halves plus 9 halves gives me negative 40 halves, which is 34 minus 20, which gives us 14. And that would give us the area of this, what's bounded here. So let me save that. And then we'll look at the next problem. Okay. Grab a drink before I do this one. So we got y is equal to 9 minus x squared, and y is equal to x plus 3. And same instructions, use an iterated integral to find the area of the region bounded by the graphs of the equations. Well, let's look at the graph here. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 1, 2, 3. So y is equal to 9 minus x squared. Looks like that. Probably should have did that in a different color, but oh well. Y is equal to x plus 3. Looks like this. And this one is y is equal to 9 minus x squared. And what we're trying to find is this right here. It's bounded by that. Well, it looks like our putting the these are already solved for y, so we'll just find out what these intersections are. What this one is right here, and what this one is right here, and we can do our x values from this value to this value. Well, this will be our point of intersections, and this one we'll have 2 here of y is equal to 9 minus x squared and y is equal to x plus 3. Because this is y is equal to 9 minus x squared, and this is y is equal to x plus 3, so it should gives us both of these. Well, again, since these are both solved for y, it makes it really easy. We'll set them equal to each other. So we got 9 minus x squared is equal to x plus 3. Get everything over one side, so we got x squared plus x plus 3 minus 9, which is x squared plus x minus 6. This factor is using a PSD. X plus 3 times x minus 2. Zero factor property, set each factor equal to 0. So set x plus 3 equal to 0 and x minus 2 equal to 0. And it looks like it's going from negative 3 to positive 2. Okay, so we're going to have, and these are our x values, so I'm going to say x equals negative 3 to x is equal to positive 2. Now our y values. Well, this y value here, this y equals x plus 3, is below this. So this is less. So I'm going to have it go from y is equal to x plus 3 to y is equal to 9 minus x squared. dy dx. If I put y's here, then this has to be dy. If I put x equals here, these will be switched around. Okay, so now we'll do the integral. So I do the inner one first. So I got x is equal to negative 3 to x is equal to 2. And this is like an invisible 1 here, so the integral of 1 is, with respect to y is just y. And I'll be plugging in these values. From y is equal to x plus 3 to y is equal to 9 minus x squared dx. So I'll put the 9 minus x squared in for the y. So I got 9 minus x squared minus, and I'll put parentheses because this minus has to affect everything that follows it, and I'll put the x plus 3 in for the y. dx. So we got x is equal to negative 3 to x equals 2. And this gives us 9 minus x squared. Negative out in front flips the sign of everything inside, so negative x minus 3 dx from x equals negative 3 to x equals 2. And I got negative x squared minus x. 9 minus 3 gives us 6 dx. Well, I take the integral of this, so we'll add 1 to our power, divide by our new power, so that gives us negative 1/3 x to the third minus 1/2 x squared plus 6x from x equals negative 3 to x equals 2. Okay, so plug in our numbers. So put 2 in. So I'll have negative 1/3 times 2 to the third minus 1/2 times 2 squared plus 6 times 2 minus, and now put parentheses because that, again, the negative has to affect everything that follows it. Now put negative 3 in for the x. So we got negative 1/3 times negative 3 to the third minus 1/2 negative 3 squared plus 6 times negative 3. Well, 2 to the third is 8, so that gives us negative 8/3. 2 squared is 4 times 1/2 is 2, so that's minus 2 plus 6 times 2 is 12 minus negative 3 to the third is negative 27 times the negative 1/3. Negative times a negative is positive. 27 divided by 3 is 9. Negative 3 squared is 9 times negative 1/2 gives us negative 9/2. And 6 times negative 3 is negative 18. So I got negative 8/3. Negative 2 plus 12 is 10. And that negative flips the sign of everything, so it becomes a negative 9 plus 9/2 plus 18. 10 minus 9 is 1, plus 18 is 19. And let me go ahead and get a common denominator of 6. So minus, multiply the bottom part by 2, top part by 2, so we got 16/6. And this one becomes multiply the bottom part by 3, top part by 3. So we got 27/6. Which gives us 19 minus 27 minus 16. Was that 11/6? And plus. Okay, I didn't look right when I wrote it down. This is a mixed number, so I'll take 19 times 6 gives us 114 and add 11, and that gives us 125/6 for our answer. Let me save that, and then we'll take a look at the next problem. Now these next problems, let me grab a drink first. These next problems are just asking us to switch the order of integration. So we're not actually finding the integral. We're going to find that sometimes to solve an iterated integral, it's necessary to switch the order. It makes it a lot easier to solve. In some cases, you can't actually find the integral unless you switch it. So let's take a look at this first one. And again, the outer one is the dy, so this is y is equal to 0 to y is equal to 3. And this inner one is the dx, so that's x equals 0 to x is equal to 1/2 y. And then we're given the function dx dy. Now, this function here isn't actually going to change when we change the this outer part here. This is our region of integration. Usually it's represented by r. And let's take a look at the graph of it first, see what in the world we're dealing with. This x equals 1/2 y. It's probably easier if we solve for y. So multiply both sides by 2. So we got 2x is equal to y. So let's see what it looks like. Y is equal to 0. That's going to be this right here, our x-axis. Y is equal to 3. Is this right here. X is equal to 0. Well, that's our y-axis. And running out of colors, y is equal to 2x. Purple. Okay. So y is equal to 2x. Looks like that. Okay, so our region we're studying, what's bounded by, is this right here. And we want to switch it. Instead of having the y equals and y equals here, we want x equals and x equals. Well, in order to figure out what the x values is, we need to find out what this point of intersection is and what this one is. Well, this one's pretty obvious. It's 0. But this one's not so obvious, though you can probably see it. So we're going to find the point of intersection of this red line, which is y is equal to 3, and this purple line, which is y is equal to 2x. Well, if they're both solved for y, so if I just equate them now, I get 3 is equal to 2x. Divide both sides by 2. And we got x is equal to 3/2. Okay, so we're going to start it at x equals 0, and it'll go to x is equal to 3/2. Again, the outer one here always has numbers on it. The part that has the variables on it, if necessary, is the inner ones here. So from 0 to 3/2. I didn't draw very well, did I? 3/2 is 1 1/2, so it shouldn't be clear out here, but you get the idea, I think. Okay, so now we need our y values. So we want y is equal to, oops, something. And up here we want y is equal to something. Now our function just remains as is. As weird as that seems, it doesn't actually change. And then this becomes dy dx. Well, let's look at our y values. This is the smaller y value because it's below this one. So this is going to go from y is equal to 2x. And then our larger one is this one right here, which is y is equal to 3. And this is our new problem, changing the order of integration. Let's take a look at our next problem. Now the outer one is the dx, so these x equals -2 to x equals 2. So x is equal to -2 to x is equal to 2, and the inner ones then must be our y's. So y equals something to y equals something. So y is equal to x squared to y is equal to 4. Of our function, and again, it doesn't matter what the function is when you're working with changing this region out here, dy dx. Now let's graph these, see what in the world we're dealing with. Y is equal to x squared. Can't draw very straight. So my y is equal to x squared. Y is equal to 4. It's going to be this right here. X is equal to -2. And as bizarre as it seems, x equals -2 and x is equal to +2 is going to occur. I drawed it real poorly again. But this is our -2, and this is our +2. And then our region we're dealing with is that right there. So from -2 to +2, and then this is the lower, and then this is upper. So that's based upon what we got written here. Well, we want to change it. Instead of having the x equals out here, we want the y equals. Well, you need to know what the y goes from what to what. And this one's pretty obvious. You can see this is y is equal to 0, and it goes up to y is equal to 4. So y is equal to 0 to y is equal to 4. And then these are going to be x equals. And then our function is going to remain as is. And this will switch and become dx dy. Well, the what color? I have no clue. We choose black. This is our one on the left side. I'll put a big L here for left side. And this, and I'm specifically talking about the y is equal to x squared. So this right side here, and then we have our left side. So our y values are going to go from this left side to our right side. So we need to find out what these are. Well, if I go to my graph, y is equal to x squared, if I were to solve this for x, drop the squared, and you put a plus or minus square root on the other side, you get x is equal to plus or minus square root of y. The left side here is the x is equal to negative square root of y. The right side here is the x is equal to the square root of y. So for this, our smaller value, which will be the one over here on the left side, is going to be x equals negative square root of y. And then the larger value will be the one on the right side, which is the square root of y. And that's our new order of integration. Now, typically in books you won't see them put the y equals and x equals. I'm just putting that there to really emphasize it until you get comfortable with it. And for me, I even still have to put that there sometimes so I don't mess things up. I find I make less mistakes if I actually put those letters there, which is kind of an important thing. If you go out and work in the workplace, they don't want you to make mistakes. Mistakes cost companies lots of money. Okay, so let's look at our next one, which is 14. Now this one's a little bit different. We're going to sketch region as area is given to it, switch the order of integration, and show that both orders yield the same area. So we'll work it twice and show that they give you the same result. Okay, so we got 14. The outer one is the x, so I got x equals 0 to x equals 6. And our inner one will be our y, so I got y is equal to x over 3, and y is equal to 2. dy dx. Well, if I draw my picture, x is equal to 0. Be that right there. X is equal to 6. There's going to be, oops, can't draw a straight line, but it'll be right there. Y is equal to 2. It'll be that right there. And then y is equal to x over 3. It'll be that right there. Okay, so the region we're working with, one to find, is this right here. That's what's bounded by those. And we'll write it the other way in a second. Let's go ahead and find the what this is integral wise. I didn't say that right, but let's go ahead and evaluate the iterated integral. Okay, looking at the inside one. We're integrating with respect to y. There isn't nothing there, so it's like the invisible 1. So again, this becomes y. From y is equal to x over 3 to y is equal to 2 dx. Plug those in then. So we got, plug the 2 in for the y, so we got 2 minus, and plug the x over 3 in, dx. And again, take the integral of this with respect to x, so the 2 becomes 2x minus 1/3, and then the integral of x becomes 1/2 x squared. Add 1 to your power, divide by new power. From x equals 0 to x equals 6. And if I plug those in, actually let me simplify a little bit. So I got 2x minus 1/6 x squared. If I plug those in, I get 2 times 6 minus 1/6 times 6 squared minus, and then I'll plug the 0 in. So we got 2 times 0 minus 1/6 times 0 squared. Well, all these zeros drop away. So then we got 12 minus 6 squared is 36 times 1/6 is 6. So we got 12 minus 6, which gives us 6. Okay, now let's reverse the order of integration. And instead of the x equals out here, we need y equals. So we need to figure out what y is going between. And it's pretty obvious in this one. It's going from 0 to 2. So that's going to be y is equal to 0 to y is equal to 2. And the inner ones now are going to be x equals something and x equals something. Well, as I look at this, the x equals 0 is my far left, so that's my smallest one. And then this purple line right here is going to be our far right one in terms of the x values. Well, the purple one is y is equal to x over 3. If I solve this for x, I multiply both sides by 3. We get 3y is equal to x. So this is going to go from x equals 0 to x equals 3y. And then this flips, dx dy. Well, again, we're working with the inner one. So that gives us y is equal to 0 to y is equal to 2. This is like, again, the invisible 1 here. So the integral of 1 is 1x, or just x. Excuse me. From x equals 0 to x equals 3y dy. So plug the 3y in for the x. So we get 3y minus, and put 0 in for the x, dy. So y is equal to 0 to y is equal to 2, and then that just is 3y dy. And so then this becomes 3/2 y squared when we take the integral of it. Y is equal to 0 to y is equal to 2. And if I plug these values in, I'm going to have 3/2 times 2 squared minus 3/2 times 0 squared. 0 squared is 0 times 3/2 is 0, so it drops away. 2 squared is 4 times 3 is 12, divided by 2 is 6. And you see I came up with the same result. So the change in the order of integration, what's on the outside here, does not affect the function at all and gives us the same result. That's what they're trying to show. So let me save that. And my eyes are bad. There. And let's look at our next problem. Again, the outer one is the dx, so x equals 0 to x equals 4. And then the inner one is our dy, so this is y is equal to x, so y is equal to 4. And got this, 5th root of 2 plus y to the 3rd dy dx. Now they give you a hint on this. It says sketch the region of integration, then evaluate the iterated integral. Note that it's necessary to switch to order of integration. If I dive right in with this, and I start integrating with respect to y, well, I could let this equal to u, but then my du would be screwed up. It just doesn't work. Well, let's switch the order of integration and see what happens. First, let's draw our picture so we can see how to switch it. So we got x equals 0, which is that right there. Got x is equal to 4. 1, 2, 3, 4. 1, 2, 3, 4. So x is equal to 4. It would be that right there. We got y is equal to 4, which should look like that. And then the other one is y is equal to x. Boy, that's a bad straight line, which looks like that. So our region is bounded by all that. Wait a minute. Try it again. Because it's this one, this one, this one, this one. It'd be this right here. So that's what we're looking at. Okay, well I want to switch this. Instead of the x equals, I need y equals here. And this one's pretty obvious. 0 to 4 is what it switches to. Now our x equals. Now again, you have to look at what it's bounded by. The far left x equals something is the x equals 0, which is this one right here. So this one will go from x equals 0. And then the far right one is this one right here, which is y is equal to x, which is the same as x equals y. And then this, I'll go ahead and rewrite this as, not that we need it right away, but this will be 2 plus y to the third to the 1/5 power. And they switch, dx, dy. Okay. Let's look at our inner one now. We're integrating with respect to y, or to x, sorry. So the 2 plus y to the third to the 1/5 is just a constant. So it doesn't change anything. It's like have 5 and a 5 there. It just stays there. It doesn't change. And the integral of x is 1/2 x squared. You add 1 to your power, divide by your new power. So that becomes 1/2 x squared. And again, this is just a constant, so it just stays. X equals 0 to x equals y. Okay. So y is equal to 0, y is equal to 4. Now we'll plug these in for our x. The 1/2, actually I guess I can put clear out in front. So put the 1/2 there. So put the y in for the x. So we're going to have y squared, and then the 2 plus y to the third to the 1/5 power just carries down, minus, and I'll put 0 in for the x. So we got 0 squared times 2 plus y to the third to the 1/5. Well, 0 squared is 0, times 2 plus y to the third to the 1/5 is 0, so all that drops away. So we're going to have 1/2 y is equal to 0 to y is equal to 4. And I got The Walking Dead on. Just seeing where they're at. Getting ready to enter the prison, looks like. Okay. Sorry, I got distracted. So then we're left with y squared here, and 2 plus y to the third to the 1/5 power dy. Well, now when I take the integral with respect to y, we use the U-substitution. So we'll let u equal to what's inside the parentheses, which is 2 plus y to the third du. 2 drops away. The derivative of y to the third is 3y squared dy. Well, we have the y squared, we have the dy, but we need a 3 in there. So we'll put 1 in there, and we'll offset it with a 1/3 out in front. So we have 3y squared and 2 plus y to the third to the 1/5 power. Okay. Well, now we can do our substitution. So that gives us 1/6. Y is equal to 0 to y is equal to 4. And the 3y squared dy gets replaced by du, and the 2 plus y to the third gets replaced by u, so this becomes u to the 1/5 du. Now personally, I like to do leave these in terms of y's, do my integration, and then plug the u equals back in, and then plug in these values. It really doesn't matter. Some people like to switch these to u values, so they'll switch this to u equals something, and this is to u equals something. That's your own personal preference. I've done them both ways. I don't see where either one's easier. Okay. So I'm going to take the integral with respect to u. So I add 1 to the power, divide by a new power. So we got u to the 1/5 plus 1, and then divide by 1/5 plus 1. Y is equal to 0 to y is equal to 4. which gives us 1/6. 1/5 plus 1 gives us 6/5, so this becomes 5/6 u to the 6/5. Y is equal to 0, y is equal to 4. Remember, if you have a single fraction down here, if you put the 6/5 down here, you flip it and multiply it times the top. And I can actually put it on the outside of the parentheses, brackets. So that gives us 5/36, I guess. And now I'm going to plug my u back in. Up above, we said u was 2 plus y to the third. So I'll put that back in. So I got 2 plus y to the third to the 6/5 power. And now plug in these values here. So that gives me 5/36. And then I have 2 plus, I put 4 in for the y. So I got 4 to the third to the 6/5 power. Minus 2 plus, I put 0 in for the y. So we got 0 to the third raised to the 6/5 power. Well, 4 to the third, 4 times 4 is 16, times another 4 is 64, plus 2 is 66. So we got 66 to the 6/5 minus 0 to the third is 0, so that drops away. So we got 2 to the 6/5. Now you could leave your answer that way if you want. If you want to put it back in the radical form, what it becomes is this is like the 5th root of 66 to the 6th power minus then the 5th root of 2 to the 6th power. Whatever number's up on top, your numerator, goes inside as a power, and then whatever number's on the bottom, your denominator, is your number goes in a slot, your index. Which means this would become 5/36 times, bring out 5 of those, and that gives us 66 times the 5th root of 66 minus 2 times the 5th root of 2. I could factor a 2 out if I wanted to simplify it. So this would become 5/18 and then 33 5th root of 66 minus 5th root of 2. And that's probably about as much simplifying as we need to do. So let me go ahead and save that. And then we'll look at our last problem. And getting tired. Getting old. I think I saved that. Sometimes I worry I hit cancel instead. Okay, 9:14. Yeah, I did. And time for that to blow up, so I'm going to bring up another copy. And let's look at this one. So we got the outer one is the y, so y is equal to 0 to y is equal to 1. And then the inner one's the x, so we got x is equal to y to x equals 1. Cosine of x squared dx dy. Okay, now if I tried to dive right in with this and take the integral with respect to x, well, I could do a u-substitution, let u equal to the x squared, but du would be 2x dx, and I don't have an x out here, so it doesn't work. Well, let's look at our region out here. So let's go from y equals 0. Here's y is equal to 0 to y is equal to 1, which is right here. And then we go from, we got x equals 1. like that. And the other one is x equals y, or y is equal to x, which looks like that right there. So y is equal to x. And this one was x equals 1. Okay. So our region here, let's see if I can get this right this time. Okay, bounded by this, bounded by that, bounded by that, bounded by this. It'd be this one right down here. So a little sliver there. Probably should have drawn bigger. Well, that's obvious. It's going from x equals 0 to x equals 1, because this is x equals 1. In terms of our y values, well, the shaded region, this bottom one, is y is equal to 0. So it's going from y is equal to 0 to this top piece here, which is the purple line, which is y is equal to x. And then the function always remains as is, and then this becomes dy dx. Because you think about it, it will remain the same. We're not actually looking at the graph of this, but the graph of that doesn't change. We're just looking at it from a different approach. Switching these around. Okay, so now we'll work with the integral. I'm integrating with respect to y, so the cosine x squared is just a constant. So really, I could even put that out in front here. We're just left with the 1 here, and the integral of 1 is y. So that becomes y cosine x squared from y is equal to 0 to y is equal to x. We went from an integral that was impossible or very difficult to one we can do very simply. So now we're going to plug these in for y. So we got x is equal to 0 to x is equal to 1. And we'll plug the x in for the y. So we got x cosine x squared minus, and we'll plug 0 in for the y. So we got 0 cosine x squared. Okay, well, 0 times cosine x squared drops away, so we're left with x times cosine x squared. And now our U-substitution works out very nice. If we let u equal to what's inside of parentheses, u is equal to x squared, du will be 2x dx. Well, we have the x, we just need a 2 in there, and we'll offset it by putting a 1/2 out in front. So I'll put the 2 in here, because 1/2 times 2 drops away. So 2x cosine x squared dx. So then we get 1/2, and x equals 0 to x equals 1. The 2x dx gets replaced by du, and I replace the x squared with u. So this is cosine u du. Well, we'll take the integral of that with respect to u, which gives us sine. So that's sine u from x is equal to 0 to x is equal to 1. We can't plug in these x values, though, until we put the u equals back in. So up above, we said u was x squared. So we're going to have sine of x squared from x equals 0 to x equals 1. Well, now we'll plug those in. We'll put 1 in for the x. So we've got sine of 1 squared minus sine, and we'll put the 0 in for the x, so sine of 0 squared. Which gives us 1/2 times sine 1 minus sine 0. Now if I look at angle 0 on a unicircle, the point there would be 1, 0. And sine is our y part, which is 0, so sine of 0 is 0. So we've got 1/2 times sine 1 minus 0, which gives us 1/2 sine 1. And that's our answer. So So let me go ahead and save that. And then I'll go ahead and stop the recorder. 13. And this will be iterated integrals and area in the plane.